Hi everyone! In this video I'm going to show you how to solve trig questions, word problems that involve finding side lengths or finding angles. So I think it's easiest just to jump right in and try solving some problems and see how to solve them, how to set them up. So the challenge for these generally is going to be in drawing the triangle. If you draw the triangle correctly, then it's just a regular, generally TOA question, a sine, cosine, tangent question that you will then solve for your missing side or your missing angle. So let's see if we can figure out how to draw these diagrams. Question 1. You are trying to calculate the height of an old tree. When you're standing 6.4 meters from the base of the tree, the angle of elevation to the top of the tree is 54 degrees. How tall is the tree to the nearest tenth of a meter? Okay, so I guess we should draw a diagram. So let's draw our tree. Okay, I'm going to Bob Ross this. You guys ready for this? Oh, beautiful, beautiful tree. Okay, so there's our tree. Okay, and there's you. Hello. Hi, tree. Okay, so there's you. And the angle from you to the top of the tree is given in the question, and it is 54 degrees. So this angle down here is 54 degrees. And it says that you are 6.4 meters from the base of the tree. So this length here is 6.4 meters. And what are we trying to solve? We are trying to solve for the height of the tree. There we go. Now we've got ourselves a nice, beautiful diagram that we can use to solve this problem. And from here, we're just going to solve this the regular way. So first thing we're going to do is we're going to label our hypotenuse. Now, this h is a little bit confusing. I've chosen lowercase h for height. That's why when I'm labeling my hypotenuse across from the right angle, I always use capital H, because lowercase h is a commonly used variable for height, unfortunately. So capital H is our hypotenuse. Now this angle that we care about is down here. So this side here is our opposite side. And then the side we're left with is our adjacent, down here. So which two sides do we care about? We care about the opposite, and we care about the adjacent. If we care about the opposite and the adjacent, it is a TOA question if you're using the SOH method. So using the SOH method, then we have tangent of our angle, 54 degrees, is equal to the opposite, which is the height of our tree, divided by our adjacent, 6.4 meters. Now the way we solve this, we're going to multiply this 6.4 in front. So 6.4 times the tangent of 54 degrees equals our height. Then plug this into the calculator, and you get the height of the tree rounded to the nearest tenth is 8.8 meters. Okay, do you guys see how I set that up? So just carefully go through with your question. Every single number you get is generally going to be needed somewhere in your triangle. And usually you're going to know two things. You're generally going to know either a side and an angle, or you're going to know two sides, because that's basically the information you need to set up one of these triangles. And for this course, it'll always be a right angle triangle. So you'll have a 90 degree somewhere in your diagram. Okay, let's try another. So you are building an accessibility ramp. By code, the ramp must have a maximum angle of 4.8 degrees. This is real, I actually looked it up. Anyway, the ramp you are installing is 6.8 meters long, and the ramp must rise a total of 55 centimeters from level. So that means like from ground. Will this ramp meet the code requirements? Okay, now this one's deliberately confusing because I've actually given you three numbers. I've given you this number here, I've given you this number here, and I've given you this number here. Now, a couple wrinkles. First of all, I noticed this 6.8 meters is different units from this 55 centimeters. So I guess I'll turn my 55 centimeters into 0.55 meters, first of all, because there's 100 centimeters in a meter, right? So we shifted our decimal place 2 spots over to get 0.55 meters. Okay, so now I've got meters and meters. That's good. My other wrinkle is I've got three numbers. There's only two of those numbers that I need. Okay, so let's go through and figure out what our numbers actually are in our triangle. So the ramp you are installing is 6.8 meters long, and the ramp must rise a total of 55 centimeters. So these two numbers are talking about your actual ramp. These are the two numbers that we actually care about. This number here, this 4.8, is just telling you the maximum allowed by code, just means like the laws about buildings. So this is just telling you that it has to be under 4.8, but it doesn't actually tell you that this ramp is 4.8. So in my diagram, I'm only going to use these two numbers. Okay, so let's draw my wheelchair ramp. So this is my ramp. Okay, here we go. And here's my right angle. Now the ramp must rise a total of 0.55 meters. So this side here is 0.55 meters. And it must be 6.8 meters long. So this side down here is the width of the ramp, but this side here is the actual ramp. Okay? Now I think that a lot of students get this ramp question confused because they confuse the width of the ramp with the actual ramp itself. The ramp itself is this. This is the ramp. This thing here is the ramp. And the ramp itself is 6.8 meters long. Okay, and then the angle must be at most 4.8 degrees. So the angle we don't know, so I guess I'll call that theta, because that's our usual variable for angles. And that is hopefully fairly clearly the angle we care about. This angle here, it's the small angle. It's not going to be this huge angle. It's 80 whatever degrees up here that we care about. Okay, so how do we set this up? Now that we've got our diagram, it's going to be the exact same usual way. This is our right angle, so the hypotenuse is across from the right angle. This is the angle that I care about, so the opposite is across from the angle I care about, and then the last side left is the adjacent. So which two sides do I care about? I care about the side that I know up here, and I care about the side that I know over here. Those are the two sides I'm going to use to solve this. Now, if using the SOH-TOA method, we need O and we need H. O and H is our SOH, right? Don't forget to pronounce that H and SOH. So there's our SOH with the H, and this tells us that the sine of our angle is our opposite, 0.55 meters, right? That's our opposite over our hypotenuse, 6.8 meters. Now the nice thing here is since we've got meters and meters, because we were very careful with our unit conversion, right? Our units cancel. And that's also, by the way, why I generally put units in here. So that I can make sure that my units actually match. If I had centimeters over meters, at this point you'd know that you've got a problem. Because if your units aren't the same, then you aren't going to get the right calculation. So now to solve for theta, we are going to do the sine inverse of that fraction, 0.55 over 6.8. Plug that into a calculator, and you get it is 4.6 degrees. Okay? So our ramp is 4.6 degrees. We haven't actually answered the question yet, though. Will the ramp meet the code requirements? It's 4.6 degrees, and it must be a maximum of 4.8 degrees. So, yes. It's up to code. Awesome. Let's try another. If you're feeling confident at this point, I'd like you to pause and try this one. If not, I'll just show you the solution as always. So you are installing a guy wire, an angled support wire, to an attachment point partway up a cell tower. So you guys have seen those before, right? A cell tower is like out in the field or whatever, and the cell tower is like really, really skinny, really, really tall. And they've got these wires that attach to the ground that go up partway up the tower to hold it in place. Usually there's 3 of those installed in a triangle around. So the guy wire attaches to the ground 12.6 meters from the base of the tower, and the angle from the ground to the attachment point on the tower is 64 degrees. Okay, nice. Only 2 numbers in this question. Makes this one a little bit more approachable. If you want to try it, pause right now. Okay, cool. And either you've done it or not, but let's move on to the solution. So here is my cell phone tower, and I've got my, all your cell phone stuff at the top. Okay, and the guy wire attaches partway up the tower. So that's my little hook where the guy wire attaches. And do we know this number? No, we don't. Okay, we don't know this number yet. Okay, we don't know that. So that's the attachment point. Oops. Okay, so that's the attachment point on there. And then the guy wire is also going to attach to the ground, right? So that's my little loop, right, in the ground. And let's make this grassy ground, right? So there's our grass. Okay, cool. So then the guy wire itself will be from this point here down to here on the ground. So if you guys see how I'm building this diagram, I'm just carefully going through, figuring out what my diagram should look like based on the idea that this wire attaches partway up this pole, this tower, and it attaches some distance away from the tower. That's all I've done so far. Okay. Now my angle is 64 degrees. So the angle from the ground to the attachment point. So the ground is here. So from the ground, the angle up towards the attachment point is 64 degrees. Okay, so that's down here. And the guy wire attaches to the ground 12.6 meters from the base of the tower. So this distance down here is 12.6 meters. All right, and presumably they want the cell phone tower to be vertical. And you'll notice that it never actually tells you that the tower goes straight up to the ground. Generally speaking, you can assume that walls are supposed to be straight, towers are supposed to be straight up. And that's often where your 90-degree angle comes in. And now last question, we are asked to, let's figure out what we're trying to solve for. We are asked for how long will the guy wire be? So then the length of the guy wire, let's do L, I guess. The length of the guy wire will be this diagonal here, the actual length of the wire itself. Okay, we've got a nice diagram. Let's solve this. So across from a right angle is our hypotenuse. Across from the angle we know is the opposite. And then the last side down here is our adjacent. So the two sides we care about are the hypotenuse and the adjacent. So hypotenuse and adjacent makes this a CAH question. CAH. Sorry, I didn't pronounce the H. Okay, so that is the cosine of our angle, 64 degrees, equals our adjacent. Our adjacent is 12.6 meters over our hypotenuse. That's what we don't know. That's the length of our guy wire. Okay, this is one where we've got our unknown side in the denominator. So I showed you last time that you can actually sort of do a double swap here. I'm going to multiply by L. At the same time, I'm going to divide by cos 64. And so that means that L is going to end up in the numerator on the left-hand side. 12.6 meters is still just chilling in our numerator on the right-hand side. And then this cos 64 is going to end up underneath. So our length is 12.6 meters divided by the cosine of 64. And you plug that into your calculator, round to the nearest tenth, and your guy wire is 28.7 meters. And if you did that on your own, congratulations. Well done. That's a tricky question. I find the students find this question confusing, particularly because the attachment point isn't the top of the tower. Although, realistically, it wouldn't really matter. If you'd drawn your diagram just with your tower going directly to the ground, right? And you said that this is 12.6 meters and this is 64 degrees and this is your length. That's actually the exact same triangle that we're solving. This extra bit up here in this question didn't end up mattering. Okay, so that's a guy wire question, another classic. The next two, I think I'll just show you how to set up. I'll skip this whole solution step. I'll give you the final answer if you want to try this yourself at the end of the video, so you can hang on for those till the end. But I'm just going to focus for the next two just on setting up the diagram for how to solve these. All right, the Leaning Tower of Pisa. And I found this picture online with a pizza slice. Pretty funny, I know. Okay, so the Leaning Tower of Pisa leans at an angle of 4 degrees. I looked it up, it's actually 3.99 degrees, but I feel like we don't need that much accuracy. So let's just use 4 degrees. So it's a 4-degree angle, the tower is 57 meters tall. What is the farthest point the top of the tower extends over its base? And we're just going to assume, you'll notice that the tower isn't actually a perfect cylinder, right? Like it's a little narrow here. We're just going to assume that it's like a perfect cylinder for the sake of this question, just to make it a little bit easier. All right, so let's set this up. The Leaning Tower of Pisa, here's my Leaning Tower of Pisa. I'm going to draw it a little bit exaggerated because 4 degrees isn't much. Okay, so there's my Leaning Tower of Pisa, and it's 4 degrees, but where is 4 degrees in this diagram? This is kind of the confusing point. The 4 degrees is like 4 degrees off of vertical. Or alternatively, if we fill this in over here, the 4 degrees is the same 4 degrees on this side. And so if that's 4 degrees, you could also solve for this angle down here, but with a note, you often only want to have one angle labeled in a triangle if you can get away with it, because as soon as you've got 2 angles labeled, it's confusing which side is your opposite, which side is your adjacent. So I'm only going to use that 4 degrees to solve this. And then the height of the tower is 57 meters. Okay, set up your right angle there. And then it's asking for, what's the farthest point the top of the tower extends over its base? So this is the top of the tower, this is the base. So the farthest point it extends over its base is this width here. And so that's the side you're trying to solve for. Okay, I'm going to go to set up another one, but I'll give you the answer to this at the end of the video. So if you want to pause and try this right now, answer is coming in a sec. Okay, last practice question, or setup question. So the maximum allowable grade of a zipline is 3%. I actually looked this up again. This is real numbers, guys. Real applications. 3% grade, by the way, if you don't know what that means, is a 3% drop. So three drop per 100 across. So in terms of metric system, that's like a 3 centimeter drop per meter of width. Okay, so actually this is actually the width, not the length. Okay, so it's 3% down for 100% across. So the maximum allowable grade of a zipline with a bungee brake is 6%. So that's for safety and speed, right? So the bungee brake absorbs a lot of your energy at the end, so you don't crash into a post and die or break your legs or whatever. So the maximum what is the maximum allowable angle for each type of zipline? Okay, so for these, I'm going to set up a zipline. And because I love Bob Ross so much, I'm going to attach my zipline to a tree. In fact, I'm going to draw my zipline between 2 trees, because that's how cool I am. Okay, there's a tree here, here's a tree here. By the way, I looked this up. Make sure your tree is at least a foot in diameter if you're attaching a zip line to it. If you're ever like trying to build a zip line in your backyard. Okay, so here's the zip line. Here's my attachment point here. Here's my attachment point here, okay, because it's going to be lower. Oops. Okay, there's my attachment point. Let's just make it bigger so it matches up. Okay, so there's my attachment point. Now, it drops 3 centimeters per 1 meter. So, in other words, if I multiply that by 100, let's just multiply that by 100 to make it into meters. So that's 3 meters drop for 100 meters across. So if these 2 trees are 100 meters across, then my drop is 3 meters. And what is the maximum allowable angle? Well, presumably we don't want the massive angle up here. Presumably we want this angle over here. We'll call that theta. And then the last thing, hopefully it's sort of obvious. If the trees are 100 meters apart at the base, then the tree should also be 100 meters across right here, right? So if we simplify that down a little bit, our diagram is essentially a 3 meter tall, 100 meter wide triangle where we have an unknown angle in the bottom corner. Okay, and our 6%, does the 6% really change anything? No, not really anything at all. All that we need to do is just make it a 6 meter drop per 100 meters across, and we'll call this beta, I guess, because let's be fancy. Okay, and you can pause now to try this if you like, because I'm going to give you guys the solutions to all three problems, the last three questions right now. The Leaning Tower of Pisa. If you work it out, your horizontal distance, your x, should have been 3.97 meters. And if you round that to the nearest tenth, of course, that should be 4.0 meters. Okay, now the zipline, the 3% line, you should have got an angle of 1.7 degrees. And the 6% line, you should have got an angle of 3.4 degrees. All right, those are trig word problems. Hope you enjoyed them.